The next important challenge when it comes to using machine learning with medical imaging is domain shift. What we mean here is mostly the distribution of the test data varies significantly to that of the training data. This means if we train a model on our training data, and when we apply this model on the test data, we see a huge drop in performance. In literature concerning domain shift, when the train and test data are from different domains and they have distribution shift, the training data is referred to as source domain, and the test data is referred to as the target domain. So domain adaptation is one of the techniques used to deal with domain shift. One popular approach is to learn domain invariant features using adversarial training. Using adversarial training, the goal is to remove domain information from features which are inputted to the classifier. So this way, at the entrance of the classifier, there is no domain shift. This is done by using a adversarial domain loss, or a domain loss here, together with the cross entropy loss, which we usually use in normal classification problems. So the domain loss actually imposes a regularization in training where it enforces the model to lose its domain information. Now, there are some drawbacks with this approach. Adversarial training is unstable, and also finding the right hyperparameters between the cross entropy loss and the adversarial loss is difficult, and it could be very sensitive to the data set. And that particular hyperparameter, this lambda factor here, actually could be very different from one data set to another data set. However, this method has been very popular with medical imaging as well as other applications of AI in vision data sets, and has been used a lot both in classification and segmentation. Here, I'm not going to go through these methods, but they are here for your reference if you need to look at them later. Another popular method to deal with domain shift in medical imaging has been domain transfer. This is more useful if we consider different modalities as different domains. Assume in one hospital we have CT images, and in another hospital we have MRI. One solution would be to train a domain transfer model to transfer MRI into CT and do both training and prediction in CT domain, or vice versa, to transfer CT to MRI and do both training and prediction in the MRI domain. So how does domain transfer or translation, here actually domain translation is the same as domain transfer. They are used interchangeably in the literature. So how does it work? Essentially, we want to learn a function f that translates an image from the source domain to its corresponding version in the target domain. And here you can see like some data sets that are used for domain translation in natural images. So a popular method is called CycleGAN. CycleGAN works by learning a function g that takes us from the source domain X to the target domain Y, and function f that takes us from the target domain back to the source domain. During training, using function f and g, which are learned simultaneously, we iteratively go from source to target and back to source, and try to reconstruct the original source image. And also we go from target to source and back to target again and try to reconstruct the original target image. It has been empirically shown that the model learns good translation functions between the two domains in this way. So one important thing to note is that the model learns bidirectional translation functions this way. It can go both from source to target, from X to Y, and also from target to source, Y to X. Right, so, So a lot of papers have proposed variations of cycle GAN to combat domain shift in medical imaging. And they have actually considered very diverse applications in this. So Wollman et al. 2018 proposes a cycle GAN-based domain adaptation approach for breast cancer classification. They use cycle GAN to transform whole slide images of lymph nodes from the source domain, which they consider one medical center, right, and to the target domain, which is another medical center, right. So that's how they construct their domain shifts. They consider data from one hospital as source and data from another hospital as target, and they use cycle GAN to kind of transfer or like translate images from the domain of hospital A to that of hospital B. And then they use a neural network for the breast cancer classification. The other paper that I would like to share with you is Manakov et al. 2019, which they actually use this cycle GAN approach for denoising of OCT images. So the domain shift here is the domain with high amount of noise versus the domain with low amount of noise. And they use cycle GAN to learn a mapping between the source, which is the center with high noise, to the target domain, which is the center with low amount of noise. This way, they achieve denoising. They can do denoising of OCT images, which I thought is actually a very interesting approach. I have the references of all these papers at the end of the presentation, so please feel free to find them later and go through these papers yourself. So one needs to be careful when using cycle GAN and actually other implicit domain transfer method. So as I was saying, using cycle GAN for domain transfer is an implicit distribution matching approach. That is because we don't enforce any direct supervision on the transformed distributions. Therefore, this may cause the image to lose some important features along the way or hallucinate unwanted features in the new domain. For example, in the image here, if you are learning the translation function using two domains, that one have a lot of unhealthy subjects and the other has less unhealthy subjects, the translated images of domain A to B may lose important pathology features. In domain 1 to 2 may lose important pathology features. On the other hand, the translated images of domain 2 to 1 may hallucinate pathology features. So this is something that we need to be careful of when using methods like CycleGAN, and we need to make sure that our subsequent model, the model that is going to that we're going to apply these transformed images on, can control for these variation of features, or these hallucinated or loss of features. So an example of this would be this paper here that it's from one of my friends, Joseph Cohen, which I think has presented in this course before. And this paper shows the effect of when using CycleGAN for domain transfer. In this paper, the domain with FLIR modality has more brains with tumor than the domain with T1 modality. So we have two domains. One is FLIR and the other one is T1. The domain with FLIR has a lot of unhealthy subjects, a lot of tumors, and the domain with T1 is almost very healthy. And when we use CycleGAN to learn a translation function between the two domains, when we translate an image from FLIR to T1, we lose the tumor. So this is somehow an exaggerated example of the type of the features that might be removed. This is a synthetic data set, so the tumors are not actually real. They are injected in the brains themselves. So that's why I say it might be an exaggerated example. Right.